Hi guys. So we're going to keep on with chapter 11. We're going to start with some vapor pressure stuff. We have to talk about boiling point, a little bit more on phase changes, and eventually we'll get into what are called phase diagrams. Woo! Exciting stuff. Again, a lot of this is review, right? So hopefully you'll remember a lot of this stuff. So last class last thing we dealt with is with evaporation, which leads us right into another property of liquids, and that's its vapor pressure. Okay, and the vapor pressure is defined as the pressure that develops over a liquid in a closed container. What I want to do is I want to actually go back to our flask that we had for evaporation. So these are the notes from last class. Right, so I want to go back to this idea right here. So if we take this container, okay, let's take an Erlenmeyer flask, and we're going to put water in there. It doesn't have to be water, it can be anything. And if we set this on the back counter, it'll start to evaporate. Right? So particles from the surface will break away from the surface, become a gas particle. The gas particle vibrate, rotate, and translate, and it actually translate out of the container, and that's evaporation, and then this will slowly go down. But what happens is if we seal this off with a cork, so that now the gas can't escape. Well, the water particles, evaporation still occurs. Okay, one of these particles have enough kinetic energy to break away from the surface and become a gas. Okay? And another one will break away from the surface and become a gas. Now, if we let this go over time, what do we see happen? Okay, well, what we start to see happen is that these gas particles, one will lose enough energy and condense back into a liquid. And we'll see this condensation on this glass part right here. And then another one will lose the energy, all right, and it will condense back into this liquid. And eventually, this comes to its equilibrium. Okay? So that we have gas particles up above, and we have liquid down below. Okay, and it's dynamic, which means it's a continuous cycle. Now, once this gas is up in here, these gas particles are vibrating, rotating, and translating, and they're running into the sides of the container wall, which means they're producing a pressure. And that pressure that's produced above this liquid is called vapor pressure. Okay. So let's write the gas particles above the liquid apply pressure. Okay, that pressure is called vapor pressure. Let's label this H2O. Now, okay, so this is my closed system. So this will produce a vapor pressure. Now, let's say that I take my container, close this whole same container, and I put it back there on the ledge in the sun. What happens to this equilibrium? Well, the temperature of this water goes up, which means the evaporation rate is going to increase, which means we're going to get more gas particles up here. these gas particles are vibrating, rotating, and translating faster. So they're applying, okay, not only do we have more gas particles, but those gas particles are applying more pressure. So as the temperature of this water increases, we get more gas particles, and those gas particles have more energy. So the vapor pressure that it produces increases. And that's a very important relationship. As we increase the temperature of the liquid, more particles evaporate, producing more gas, which increases vapor pressure. Okay. So we have this direct relationship between temperature and a substance's vapor pressure. Now, what's the relationship between strength of intermolecular forces and vapor pressure? Well, let's say that this has very strong intermolecular forces. If it has very strong intermolecular forces, it doesn't want to evaporate. If it doesn't want to evaporate, that means we're going to have fewer gas particles. If we have fewer gas particles, that means we're going to have a lower vapor pressure. All right? Well, what if we have a substance that has very weak intermolecular forces? Well, then it's going to evaporate very fast. It's going to be easy to evaporate, which means we're going to have lots and lots and lots of gas particles. And if we have lots of gas particles, that means we're going to have a very high vapor pressure. So the stronger the intermolecular forces, the less vapor pressure produced. Okay, and that brings us to another term, and that's volatile. Okay, if something's volatile, these substances evaporate very quickly because they have high vapor pressures. If it's a volatile substance, that means it has weak intermolecular forces. I use IMF for intermolecular forces, Okay. Now, a perfect example of this is why you should not pour gasoline to start a fire. Okay. Gas. Okay, so gas is made of organic compounds, which are all nonpolar, which means these all have dispersion forces. Okay, these dispersion forces are very weak. So that means gas is going to evaporate very quickly. Okay, it's volatile. Right? So now what happens if you try to start a fire with gasoline? You pour the gas, let's say we're trying to start a campfire. You pour the gas on the wood, right? You go ahead and put the gas container down, and then you grab your matches, all right? And then you light the match, and then you put it onto the fire. The problem is that whole time that you're putting the gas container down, you're getting your matches out, you're lighting the match, this gasoline is vaporizing, okay? It turns into gas vapors very, very, very quickly because it has very weak dispersion forces, all right? It has a very high vapor pressure, all right? And this gasoline turns into gas vapors. Now remember, what does that gas do? It expands to fill its container, all right? Now, as soon as you light that fire, the gasoline vapors are also going to light, all right? And that's how people get burned really quick, all right? So you got to be really careful with volatile substances, and gasoline is one of them. All right. So in general, this is a general. Liquids with large molar masses okay, so liquids with large molar masses, okay, these will have lower vapor pressures. Why? We've got to do those intermolecular forces again. Okay, so the bigger our mass, the more dispersion forces we have. So remember, the greater the strength of those forces, the lower the vapor pressure. So what if we have liquids with hydrogen bonding, like water? So liquids with hydrogen bonding will have lower vapor pressures and substances of similar mass that do not have hydrogen bonding. Now, we dealt with vapor pressure in regular chemistry. And in the reference table, we had this chart. And we had table H. And this gives us the vapor pressure of 4 different liquids. Okay, so here's my temperature, here's my vapor pressure that substance produces. And we said as our temperature increases, the vapor pressure above it also increases. Okay, oh, hold on. So what's happening is our vapor pressure increases, our temperature increases. Now we know something about these now, right? Which one of these is going to have our strongest intermolecular forces? Okay. Well, this one right here is going to have our strongest intermolecular forces, right? And this one will have our weakest intermolecular forces because of these vapor pressures that are produced. All right, good. So that brings us to what's called boiling point. Okay. And the boiling point is the temperature at which the vapor pressure of a liquid is equal to the external pressure. So boiling point is really looking at external pressure and vapor pressure. Our normal boiling point is the temperature a liquid boils at standard pressure, or 1 atm. So water's boiling point, I should say normal boiling point, is 100 degrees Celsius. At this temperature, the vapor pressure is equal to external pressure, which is atmospheric pressure. So let's say we have a pot, and we have water in it. If this water is at 50 degrees Celsius, the vapor pressure that it produces, and we could look at this chart real quick, or we could just look it up, is about 10, 20, 30, 40, 50. So this is about 13 kPa. Well, our external pressure is 1 atmosphere, or 101.3 kPa. So the pressure pushing down on this is 101.3 kPa. The vapor pressure, or the pressure pushing up, is only 50 kPa. This will not boil. So what do? Well, we raise the temperature of this water. Okay, so if we take our pot, we heat it up to 100 degrees C, it raises the vapor pressure to 101.3 kPa. So now the pressure pushing down, or external pressure, is equal to 101.3. So this will boil. Now, remember, boiling is really this equalization of the external pressure and the vapor pressure of the substance. So can we make water boil at room temperature? Which is about 23 degrees C. Okay, so if I have a pot of water and it's at 23 degrees C, can I make it boil? Well, the answer is yes. How? If I reduce the external pressure, the water will boil. It doesn't mean it's hot. It's not hot. Okay? It's not hot. It's only at room temperature. The water's temperature doesn't change. What we're changing is the pressure pushing down. Now, how would we do this? Okay, well, if we put the water in a flask and I sealed it, okay, and I put a pump on it so it pulls out the air, I can reduce the external pressure. And then this will boil at room temperature. All right, so let's hold there. I'm going to stop this video for a minute and we'll pick up in a minute. So just hold on a second.